Okay, should be the last video. We'll do one more explicit case of an individual sequence, individual column, and then we'll go for the gusto and prove it in general. Okay, so this time I'll try to remember what I'd really like to show, just so I can clear the fractions out. 0 plus 0 plus 0, and then it finally starts 1 plus 4 plus. Okay, and I'm going to multiply everything. I'm just going to multiply everything by 4 factorial. 4 factorial over 3 factorial, well, everything cancels except for the 4. So what I really want is that, oh yeah, and these are going to be multiplied by 4 as well. They're not really going to show up explicitly though. Okay, so if I multiply everything by 4, or 4 factorial, oh my bad, that's a 24, and that's a 96. Okay, so I multiplied everything by 4 factorial just to make things a little prettier. And I want to claim that that is just exactly n minus 1, n minus 2, n minus 3. Okay. I'll put it, yeah. Okay. And the base case is done. We check this works in the first few cases. Okay. Inductive hypothesis. Assume. We're just going to assume that this is true for K. Do a little cut and paste. So we want to know that no matter what K is, if it's true for that one K, if we happen to know, somebody checked it where K is 367, can I show for 368? If K is any particular number, just taking one at a time, can I show the next one? If I can do that, and I know the base case, then I know it's actually true for all positive integers at once. Okay. And then to show inside the inductive hypothesis. So this is the thing we want to show in general. And then maybe I should like indent this some more or something. Here's what I get to assume temporarily, and given that assumption, I want to show the next case. Okay, so that's going to be the same thing where every single k is turned into a k plus 1, but what does that do to the summation? It makes it one longer. So that's going to be plus for k minus 1, k minus 2. I'd like to show that that's equal to, it's getting kind of long there, equal to this where the k becomes a k plus 1, k minus 1 becomes a k minus 2 becomes a k minus 1, and k minus 3 becomes a k minus 2. I won't write it out just to be able to save a little time. That's p of k, that's p of k plus 1. Okay, so now we can do the proof. We just look at this guy, this whole summation. I'm just put it on the next line. Okay, we know that everything except the last term is exactly something we know about. Okay, and then it's just plus one more thing. K minus 1, k minus 2. Once again, just like the other ones, there's a huge common factor here. It's all got a common factor of k minus 1, k minus 2. Hello. And then times k minus 3 plus 4, which of course is equal to all this stuff times k plus 1. And that's just in a different order. That's what we wanted to show. It was the next product of those consecutive integers. K plus 1, k minus 1, k minus 2. Okay. So that completes the inductive step. And hence, the statement is true for all positive, well, non-negative integers, because we checked it for 0 as well, and by induction. Okay, now we've really warmed up well for the general case. Okay, hopefully this was almost boring. Hopefully you did this with no problem because it's so similar to the previous ones, but you know, these are tricky things. It can be a challenging topic. Okay, so now we want to show, let's just parse what I've written here even. Okay, it's the summation. So we pick an R. The R really tells us which column we're in. So the R is the column, and the K is the rows. Okay, so if we go back to the original table, when r is like 2, for example, then that's this thing. This is the sequence when r is 2 and k is 0, 1, 2, 3, 4, 5, 6, 7, 8. And I'm summing those guys up, and the claim is I get like if I sum these folks up, I get the next entry in this table right here. Okay, so how does that work with summation notation? Just to introduce a little bit more sophistication in how we're writing things. Let's come down. Okay, so here just means sum up the general formula that we know is true. So we're going to assume that we know that we're interested in this kind of formula for a sequence, and with consecutive products on the top and a consecutive product on the bottom, a factorial on the bottom, and I sum those up going k equals 0 to n minus 1, is it true that I get what is essentially the next step in that sequence? Again, a consecutive product of terms, but one more. Notice this went k down to k minus r plus 1. This goes from n all the way down to n minus r. So if you count how many things there are in here, there's going to be r plus 1 things on the top and r plus 1 on the bottom. Okay, let's see. So the base case, here, the base case, we haven't done all of these because we didn't do an infinite number of rows or columns in our big table. It's the top of each column, but we didn't do all the columns. Okay, but the base case is still easy, okay, because if n equals 0, let's just do two base cases in case we're paranoid. N equals 0 means the sum is empty. And the right-hand side gives 0. An empty sum gives 0, and the right-hand side clearly gives 0 when n equals 0. So we're fine, okay? If we're a little worried about empty sums, and that could be a little tricky, just to be a little more careful, n equals 1 means, okay, what's the sum? It's going to be sum equals k equals 0 to 0. There's really no summation. It's just one term, okay? The left-hand side is just going to be one term, and it's going to be 0. It's just going to be 0 still. So the left-hand side is 0. And the right-hand side is still 0 as well, because there's n minus 1, and that's going to be 0. Okay, so we're really okay with the base case. They're degenerate in every single example. Okay, inductive hypothesis. We're going to assume, and I think I thought about this and then I forgot when I started writing this down. I'm using k for a different thing here. You know what? I forgot that I have been reserving k. Let me use L for the version of n that we use when we're trying to emphasize the difference between the fact that we're in the inductive step. So let me change that to an L. So the thing about dummy variables, they don't have any meaning outside of the sum. They're just a temporary convenience for labeling what the formula, the pattern that you're summing up. And so I can just change those as well, at will. Okay, so in my inductive hypothesis, I'm going to change this n to a k. Okay, and then this is going to be k. Okay, so that's what I'm going to assume, that it works for a certain r. Okay, and going up, or for any r, and going up to k minus 1 there. And then to show, I want to push that where k gets replaced by k plus 1. Ooh, I didn't put it in the right place. Okay, you can see with the summation notation, it does make it feel a lot harder. But everywhere I have a k, I'm just going to put in a k plus 1, or in other words, k minus 1 changes to k. The cool thing about summation notation is that's the only change I actually have to make here, because that exactly says take this summation 1 further, and that's what we were doing in the previous examples. Now over here, it's a little more work. K plus 1 times k minus 1, and then this is going to be k plus 1 minus r. Okay. The r doesn't change at all. I'm not doing an induction in r here. It's going to work no matter what the r is, and that's the kind of cool fact. Okay, So how do I show that? Proof. All right, I'm just going to do exactly what we did before. It's really good to go back to the previous examples, scroll back or rewind a few minutes or look back up in the PDF and see how this really does correspond, even though we're packaging things up with the summation notation, to what we did before. It looks more complicated, but it really is very similar. Okay, so here's the key. The absolute key to making induction work was that the summation in the next version was just the old summation plus one thing, and that's true here too. A summation up to k, you can say, well, I don't want to use the summation notation for every single thing. I like the summation notation idea. It makes it very compact and everything, but I'm going to do it all the way up through k minus 1, and then, I probably need to put this on a new line, then I'm going to do the last one by hand. Okay, so that just means I'm going to put k, ooh, and I forgot my usual hint. Okay, and I'm going to fix it up with my usual hint in a minute. You might have been wondering, why isn't he using that usual hint? Okay, k minus 1, k minus 2, k minus r plus 1. Okay, so just to avoid a tiny little bit of dancing with common denominators, okay, I'd like to show, okay, I'm going to show that I'm going to multiply everything by r plus 1 factorial. So I'm just going to take that out. So I guess I'm taking out the fraction. Because what we were able to do is we were able to come up with something with no fractions on the other side. Now if I multiply this by r plus 1 factorial, this whole thing times r plus 1 factorial, well, r plus 1 factorial is r plus 1 times r minus 1 times r minus 2, etc. This is r times r minus 1 times r minus 2, etc. So the whole thing just gets an r plus 1 on the top. And so again, clear the fractions. Okay, that's what I really want to show. Okay, so now I'm going to do the same modification here. It's probably honestly not worth it, but just I have this affection for doing it in this way where you don't have to deal with any fractions after you clear them here. Okay, that's what I'd like to show. Okay, and that's the inductive hypothesis. That's what I'm assuming I know. And then here, it's the same thing going up to the k, and then here it's just that without the fraction, without the denominator. It's just the numerator of this guy. Okay, so hopefully you've been going to get a nice cup of coffee while we've been doing this. All I did was I multiplied everything by r plus 1 factorial on each side. Okay, so now the proof is, I'm going to start over here. Okay, is that this thing, the big sum, is the previous sum, where I just went up to k minus 1, plus the last term, which is just with the k actually put in. This one's getting long. I should have done this in 2 parts. No biggie. As I said, you could take a break in the middle. Okay. Finally, I'm ready to use the inductive hypothesis. This is none other than the previous case of this sum. Okay, and that's this guy. Oops. This guy totally... That guy totally went away. There we go. Oops, sorry. Okay, that's what happens when I edit on the fly. Okay, that's where we're able to use this inductive hypothesis. The sum up through k minus 1, multiplied to clear the fraction, we know that that's just k times k minus 1, etc. Okay, and now we're really home free. It's going to look very similar. I know there's more letters. It's more challenging with this stuff. But look what we got. We've got something with a huge common factor. We've got k minus 1, k minus 2, dot, 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 okay, k minus r plus 1. Okay, so in here, one of those things, what's the second to last term here? I got to match these really carefully. Oh, if I'm counting down, and the last thing I got to was k minus r, I can count back up by 1. Oh, there's a k minus r plus 1 hidden in there that really helps to make explicit. Okay, so there is a common factor of all this stuff. And what is it multiplying? In this case, it's k minus r. Just like we had like k minus 1 or k minus 2 or k minus 3 in the previous cases. But then plus, okay, then it's also this common factor times r plus 1. Woo! The r's cancel. And I'll bring the k plus 1 in the front. K minus r plus 1. And that's exactly what I want to show. Okay. Really good to look through this carefully and match it step by step with what we did in the previous cases, because it really is just exactly that, written out in a way that says, you know, this is still going to work no matter how many terms I have in this product. Now, if you want to be super careful, anytime you have a dot, 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 I mentioned this in another video, anytime you have a dot, 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 we're kind of secretly hiding another simple proof by induction that this pattern, these kinds of computations really work the way they are advertised to do. But it's the kind of proof by induction that nobody is ever going to force you to do, because it's a fairly obvious pattern. That, yes, we know what's hiding in here. It's really obvious. It's just all, well, not maybe obvious, but it's all the consecutive integers between k and k minus r plus 1. Okay, but there we go. That's what we wanted to show. So we would just wrap it up by saying that something like this completes the inductive step, and hence the result is proved for all non-negative integers n and all non-negative integers r. That this works for all columns at once. What we've seen is that no matter what r works, no matter what r is, this kind of proof works, and we did it all at once for all columns, all rows, and the whole thing works finally.